is mass times velocity?
It's 2 and 4, 5 and 3.
So you're good with that, but that should be. That's actually gonna be like 2, that should be good. Something's still off. All right. Oh. Mass times velocity, mass. C and D are velocities. So it's 2.
Ooh, hey, yeah.
Yeah. Five is the two.
Yeah, but the first, is that first? Oh, it's 4.
Yes. That is.
I guess
it's split.
Oh, yeah. So like this part's like G kind of right here. So could I just like, I guess, recognize that obviously this one's from this one. This one would be like the momentum force and this one add together. Then the same thing here, but substitute this one in the D for that one. Could use like, I guess that.
So all right, so that's the momentum equation right there.
Yeah.
And this right here, I mean, what I was trying to do is justify some of this. The whole relative speed of approach equals relative speed of recession. So, I mean, if you got this down, jump straight to it. All right, so perfectly inelastic, that's right. And then where's this one too? That's perfectly inelastic collision right there. I'm good with that. And then you basically rederive.
Yes.
Where'd you get this?
He gave me that. Then I just use that. Software.
Yeah, D equals C plus 1 is not correct.
So that's probably where I'm wrong.
Yeah, it would be, the equation right here would be the. So it's 5 minus -3 equals D minus C.
Well, I found D first. This equation, I got. Is that the same as this A minus B? B minus C. Which part is okay? I have the 4 divided by 12. Yeah. Let's see. I don't know what happened with 6. But what's that? 4 divided by 12. That's what I'm taking from there. Yeah.
I'm gonna go, make sure I have the solutions for 7. I'm gonna list the solutions for master set 7, and then I'll be back, and then we'll talk about this and move on to the next thing.
When is the next master set due?
Oh, we need to establish that also. So you've got, let me do this thing and then we'll get to that too.
The mechanical energy?
Yeah, whatever you say, like A is pretty much this 5 minutes.
I really want to finish the last.
This is your. So just add 5 and -3.
So we can have time.
Plus -3 is 2.
Like,
That's for this one. Yeah, I can get it.
But I haven't even started the mechanical energy.
I was going through that.
Two C.
Yeah, probably there is some thought. Depends on what the beach is.
Two C plus four is the same as the two times the velocity, but we just substitute this C right here. And then this is saying that the mass times speed is the velocity.
I think they're half on the beach, so you can like have bonfires, that's on the beach.
Oh,
I'm
two.
pretty sure it's a little cold though.
Oh, but I feel like I'm facing the weeds. So that's
All right, so let's talk about a couple things here. First off, I haven't scanned master set 7 solution yet, so I'll need to do that.
That's like this right here. Ignore this one. That's like this one.
I want to, just out of curiosity, of the 3 techniques, one of them involved using the quadratic formula, one of them did the relative speed of approach equals relative speed of recession, and the other one was shifting of the reference frames. Who did the quadratic formula approach? Method 1. That's 2. Who did the relative speed of approach is equal to relative speed of recession? And shifting reference frames? Which is one of the reasons why I go over all 3 techniques, because I've never had a class, actually, I changed that. I think I've had one class that zeroed in on one, because they work so closely together. But the answer's right here. I don't want to go through all 3 techniques, but method number 3 is the fastest. Once you establish the one-dimensional perfectly inelastic collision velocity, we start at 5 and 3. This is the lab frame. We shift by subtracting -1/3. And this puts us into the 0 momentum frame. So that's that's 16/3 and 8/3. We then collide. They switch signs. That's negative there. It was positive 8/3. And then we shift back by adding -1/3. -1/3, which makes that 7/3. And -17/3 meters per second. The other one is a matter of setting up the equations. We have the total momentum beforehand, 5 times 2 times 5 plus 4 times -3, which is -2, which is equal to 2c plus 4d. And then the relative speed of approach equals relative speed of recession. We end up with 5 minus -3 is equal to d minus c. And those are the 2 equations we're working with there. And, at this point, you're all in Calc 2 or later. Plenty of places for Carol's errors, as some of you decided to explore during this.
How would something like this change if it was a 2D problem? Because wouldn't it still just like hit each other like?
Yeah, all right, so I want to address the 2D problem and the imperfect collision also, so we'll get there and we'll set it up. We'll not necessarily work through an entire problem. And then method number 1, you still have -2 is equal to 2c plus 4d. But you'll also have the 1/2 2c 5 squared plus 1/2 4 3 squared is equal to 1/2 2c squared plus 1/2 4d squared. And so you'll have these 2 equations, method number 1. Kyle, you want to ask a question?
No, I was.
Okay.
On the hand quiz.
All right. And at this point, it's a math problem. All right, questions before we talk about the imperfect collision and just the joy of doing that? Jesse?
So why is it 5 minus -3? Right there where it says D minus C? Yeah, cause I got 5 plus -3, that's right.
All right, so when you're doing the technique number 2, the second equation, A minus B is equal to D minus C. Recognize these are velocities here, even though I didn't put the vector symbol over it, these are velocities. And if to the right is positive, I wrote 3 meters per second to the left, but in terms of a velocity, it would be negative 3 meters per second. And so that's why, so V for initial is negative 3 meters per second, which is labeling as B over there. Is that sufficient?
Yeah, okay, I see.
Now I did one of these, I've done this before where I set it up like this. For some reason, I just like them colliding into each other. And then I gave one to the class where I had more pursuit instead of straight on collision. So I flipped that around, and that really messed people up. So please be aware of, direction matters. So 3 meters per second to the left is very different than 3 meters per second to the right initially. And then you get in the whole bit with, for the beginning of Mad Max Pursuit. If you haven't seen Mad Max, I'd recommend it, but not for the kids. All right, questions? All right, so imperfect and 2D. So we'll start out with imperfect. Let's keep the same setup there. We do have to give one other piece of information. Either I need to tell you one of the velocities after the collision, or I need to tell you how much kinetic energy is lost. So lose 30% of kinetic energy. There is no nice shortcut here. At least not that I've seen. So we still have our conservation of momentum problem. Collision, conservation of momentum. So we still will start out with -2 is equal to 2c plus 4d, just like we've done before. The second one, we do have to use kinetic energy equation. So I know initially we have 1/2 times 2 times 5 squared plus 1/2 times 4 times 3 squared is equal to, well, it's not equal to the 1/2 times 2 times c squared plus 1/2 times 4 times d squared, because we lost kinetic energy. So if we lost 30%, how much did we save?
Well,
I thought I was in calculus too.
Yeah, let's go with that. I think his name was Grandinst. There's something called a Grandinst prime, where brilliant, incredibly abstract mathematician, considered to be one of the most brilliant mathematicians of the day, was asked to name a prime and he said 42. It's known as a Grandinst prime because it's not really a prime, it's just, some minds are just way up here that, it's difficult to move them down here. So we retained 70% of what we started with. So 0.7 times our initial amount is equal to the final amount. So we have this initial factor. So we can actually still come up with a number here. So that's 0.7 times 25 plus 18 So 0.7 times 43. 30.1. Equals c squared plus 2d squared. So you're basically using technique number one. You're gonna get two solutions. You don't have the non-collision solution because we have introduced that we're gonna lose 30% of what we started with. So, it's just math. Plenty of places for just fun errors. -1 is equal to c plus 2d. So c is equal to 2d plus, try that again, equals -1 minus 2d. Plug that in, 30.1. All right, and I still see this occasionally. I see it more often than every time I see it, I'm going, whoa, I'm just surprised by it. When you're squaring a binomial, it's the first number squared plus the last number squared plus 2 times the product of the two numbers. It's not just the first squared plus the second one squared. There is another term. So this is 1 plus 4d plus 4d squared plus 2d squared. And so we end up with 6d squared plus 4d minus 29.1 equals 0. And it's quadratic formula time. You will end up with, unless I made a careless error, 2 positive solutions. Now let's run it through, see what we get. First, double check the math here. So, you divide 30 by 2, so -1 is c plus 2d. So c, subtract that over that, plug that into there. So the first one squared plus 2 times the product plus the last one squared. Then I have that, so I have 6d squared. Subtract that over. Then, what are the two solutions? No, we will have a positive and negative solution.
And I'll say something wrong, I think the
Wait.
positive is 2.56.
Why is it 30.1 equals c squared plus 2d squared? Wouldn't it be 60?
Our initial amount of kinetic energy was 43 joules. And we lost 30% of it. So in other words, our final amount is 70% of what we started with.
Yeah, but wouldn't you, never mind, I think it's wrong.
Okay.
I got that as my negative function.
I got that up.
Yeah, I did it, that was something wrong.
Negative 2.56, okay.
For my positive.
1.9? 8.9.
Yeah, I just wanted to know in this method why you equalize to 0 to solve it, and forget about the 30.1 in your quadratic.
Like, how did I get here?
Yeah, I mean, I know that you're solving the right part, no?
The right part gets me to, that gets me to there.
Uh-huh.
And then I subtracted 30.1 from both sides.
You got, oh, sorry, I didn't see that part, okay.
Okay. So, and then that puts me. All right, so I have two solutions here. Oh, another question before we talk about the C? All right, so that's D right there, and so C, -1 minus twice that. So twice that one would be 5.12. So this would be 4.12 meters per second. And then 3.6378 negative 4.78. So, again, as always, unless there's Carol's error, one of these solutions is the correct answer and one of them is not. We're done with the math part. Now it's time to think of physics. Which one is the correct solution and why? Again, so it's those two or those two.
The negative and then the positive?
This one is, you liking this one?
No, it'd be the negative and then the positive, or not, it would be the negative 2.56.
That goes with this solution up here. You think it's this one? Why this one?
Because if
After
it's,
they collide, they're gonna bounce back.
You have a different reason?
I think it's just because it's closer to their velocity, like for the initial. Like if 5 and 4.78 are like kind of closer. And also what he said.
All right, let's see, what does a negative velocity mean?
It's going to the opposite of that.
Define your coordinates.
Okay, and we define positives that way.
Yeah.
So negative means it's going that way.
Yeah.
So if the first one is true, that means after the collision, the 4 kilogram mass is going 2.56 meters per second to the left, and the 2 kilogram mass is going to the right at 4.12 meters per second.
The second one cannot be because is passing through one of the other ones.
You said the second one?
Yeah.
Actually, it's the first one.
No, in the first one, in the second one, you got the first one continue positive, and continue negative. Then they pass through each other and continue.
Yeah. Be careful. This is D right here. This is the second mass. This is
this is the second. Okay.
yeah. We saw. So it's sort of presented backwards here.
Sorry, then exactly the contrary.
So the first set of solutions is this one. They collide, and the 4 kilogram is still moving to the left. So that is not going to happen. And then the second solution is the 2 kilogram is going at negative 4.78, so 4.78 meters per second. And the 4 kilogram, 1.89 meters per second. This has some physical possibility. Once we get to quantum physics, the first one has a physical possibility, but that's not classical physics, which is what we're doing right now.
So for neither of the conditions, they would never go through each other, just two-sided.
Not at this point. No. Although we could have one smash into the other one and one of them break up into pieces shooting off into different directions.
How would we know that?
I'm gonna have to tell you. Well, for some reason, one of my favorite questions when I was teaching high school a couple decades ago, the thing's in the air and it explodes. And one piece lands in one spot, where does the other piece land? Maybe we should resurrect that one. All right, so that's the imperfect collision. Now for the two-dimensional. Oh, by the way, so this is, oh, and also master sense, we need to talk about that and return stuff. So chapter 11 is basically what we're doing right here. Yes. All right. In the summary section, the equations that I usually give you are the ones that are in the summary section or special cases, this kind of stuff. This is page 324. I will tell you that the equations next to 1 and 2, these are 3 equations right here, I am not going to give you. Just letting you know. The trouble is I've given formulas like that before, and I find students misapply them. They stop thinking and it's just through straight plug and chug. I've had more students get it correct after I stopped giving those equations than when I did give them.
So equation 11.13.15.
Yes. Those I will not give you.
Wait, what was that again?
Equations 11.13, so basically, those 3 equations right there.
What page is that?
Equations on page 324, under special cases, equations 11, 13, 14, and 15.
Austin, send that in the Discord. Austin, send that on Discord. You didn't hear me? Alright.
Yeah, it just, in my mind, it leads to lazy thinking. Now, part of that sort of defeated because the last test will be at home, but the quiz will be here.
Wait, so this is all part of the last test?
Yes,
So there will only be 3 tests?
4 tests.
So what's the 3rd test?
The third, you remember that multiple choice test you took the first day?
Oh,
We'll do that again at some time before Thanksgiving.
Is that like, isn't that like Newton's law?
Pardon?
Isn't that like Newton's law?
Yeah, I mean, we could do it now. I tend to do it after we finish with the momentum stuff.
How much stuff is gonna be on the last test then?
How far do we get? Energy, momentum, rotational motion,
simple one.
harmonic motion. What was the last thing you said? Oh, you were guessing?
What?
I was trying to figure out the last thing you said.
I said I don't like simple harmonic
Oh, this is all to spite Precious.
motion.
Time flies.
Indeed it does.
So electricity and all will be in the 2nd semester,
Right.
All the cool stuff.
and the harder stuff.
You're a future electrical engineer?
No, computer science,
Oh.
software engineer. But I've been thinking about minoring in electrical engineering or physics, one of the 2.
It ultimately comes down to how much theory do you like and how much practical application do you like, I think.
I think I'm leaning towards application, so probably electrical engineering.
Yeah, I was, like, undergraduate degree is mechanical engineering, and I always felt it was missing more of the basis behind it.
At least we can set up a two-dimensional problem. And then master sets, assignment, and hand stuff back. Oh, why not keep the same scenario there? So afterwards, the 2 kilogram mass goes shooting off like that at some angle called theta 2, and the 4 kilogram mass goes shooting off at some angle there called theta 4. All right. Regardless of whether kinetic energy is conserved or not, and I typically throw that in there, but we do have 2 equations that we can pull out of this. Because momentum is conserved, it's a 2-dimensional problem, which means that I have P initial x I hat plus P initial y j hat is equal to P final x I hat plus P final y j hat. I mean, it's a vector, I can break it up into coordinates. And whenever you have 2 equations with unit vectors like that, well, they have to match up. The I hats have to be equal and the j hats have to be equal. In other words, Pix must be equal to Pfx, and Piy must be equal to Pfy.